Here we go.
So I'll start sharing.
Yeah, I'm going to just give a quick intro, and then we'll let you start sharing, or you can share now. Okay.
Okay. Yeah.
All right. So good morning, good afternoon, and good evening. Welcome to our November-December UI Assist webinar. And today we're honored to have some of our students that participated in internships in the summer of 2022. So we're going to start with presentations by Satabdy, Jena at Roorkee, and Partha, Sarker from WVU, with support from WSU, WVU, and IIT Roorkee. And then our second presentation will be by Piyush Sharma, who is from IIT Kanpur and worked with Dr. Sanjeev Panala at WSU. So I'll turn it over to you, Partha.
Yeah. So hello everyone. For the first part, Satabdy will mainly go through, and then I'll go through the cyber part. Satabdy, please.
Thank you, Partha. Good afternoon, good evening, and good morning. We did this work at WVU during the summer internship. It revolves around real-time modeling, co-simulation, and cyber-physical analysis for interconnected DC microgrid clusters. Next. This is the research team. Next. The outline of the talk would be discussing a little bit about background, the test system structure, the cyber layer, the control layer modeling. The co-simulation part would be done by Partha, cyber attacks and the communication layer modeling, and then we'll move towards results and discussions and conclude it. The background is a little bit about cyber physical structure. Why do we need such CPS systems? Is that because our distribution systems and autonomous microgrid structures are rapidly evolving with the unprecedented deployment of smart grid technologies, Internet of Things, ICT business models, and addition of new stakeholders, and as such, to incorporate all of them together with the electric power grid or isolated structures, microgrid structures, we need physical layer integrated to cyber layer, but on the surface it just seems to be two entities, that is just physical layer and cyber layer, but it also involves human interaction in between. So that's a little background on that. Next. To control these CPS microgrids, from the perspective of microgrids, generally distributed hierarchical control is getting more and more evolved, and the different parts of distributed hierarchical control include primary control, secondary control, and tertiary control. So just a quick description. Primary control, it controls the sharing of local power, voltage, regulation of voltage, and local load current sharing. And it is normal primary control for converters that we use. Secondary controller is built on top of primary controller, which is used for sending compensation terms to the primary controller to work upon them and get more accurate power sharing and more tight voltage regulation. And tertiary control has a little bit duality nature. For example, sometimes it's used for dynamic optimization, sometimes it might be used for getting power sharing between inter microgrids, or it can be used to receive set points from operators. Next. So when we discuss primary control, group control is one of the possible solution for primary controllers in microgrids. And how does it work? It It works on reducing the DC voltage reference with increasing load current. And with the help of Droop, we can achieve accurate current sharing according to proportionate to the power rating of the converters. How is that realized? It is realized through a virtual resistance behind the source. And that's how we get the power sharing accurately proportionate to the uh, current rating of the converter. But there is a trap. When we try to achieve accurate current sharing, we cannot regulate the voltage because there would be a voltage drop across this virtual impedance. And hence, the role of secondary controllers come into action, that means it becomes important. Next slide. Yeah. And in order to evaluate these upper layer controllers that we design, which are above the primary controllers, the structure for them is either centralized or distributed. So in centralized, these converter agents, or we might say microgrids, clusters communicate to a central server, and hence there's a problem of single point of failure. However, in case of distributed algorithms, what we do is these microgrid clusters share the information with each other to the nearest neighbor, and hence we reduce the we alleviate this single point failure problem. Next. So let's get into the cyber-physical structure that we have taken into consideration. Here on the slide, we can see that we have taken up interconnected microgrid clusters, say n in number, each of them consisting of, say, SK converters. Yeah, then we will, next slide, please. We'll get into the cyber layer. The cyber structure here has been used to basically focus on one important thing, that for every microgrid cluster, we have used one of the converter agent as a pinned node. Pinned node in the sense that it becomes a virtual agent for all the layers that we design above the secondary layer. And hence the pinning matrix, which is P1 in this slide, is a non-zero diagonal matrix. For representation purpose, it's just one. Next slide, please. Control layer modeling. We'll just have a quick brief through to the slides. Yes, we actually took up two types of control structures. We took proportionate power sharing and dynamic optimization among these clusters. This involves a lot of mathematical equations, but to simplify it, there is a local tertiary controller, there's a global tertiary controller, then there's the secondary controller, and there's a primary controller. So basically, primary and secondary controller helps in intra-microgrid objectives, achieving the intra-microgrid objectives, whereas local tertiary and global tertiary help us in achieving the inter-microgrid objectives. Next slide. Yeah. Same way, this process being used for equalization of the incremental cost. In this, we try to have simultaneous voltage synchronization as well as dynamic optimization. So the optimal regulator that we have designed on the figure in the far right of your screen is for satisfying the non-equality constraints that we have taken. And the voltage observer helps us in maintaining that equality equation of balance, meeting the demand and supply balance. And from this is a part of our work has been published in PyCon as well. Next slide, please. Okay, these are the equations that govern the proportionate power sharing, and similarly, quite similar are the equations for equalization of the incremental cost or the incremental or the energy price. just only one substitution is done, that instead of current, we substitute lambdas or the incremental costs. Next slide. So from here, Partha will pick up. Partha, please.
So yeah, as Satabdy said that we all did all this simulation in real-time co-simulator platform. Here we used a real-time digital simulator, that is RTDS. And in the RTDS, all these mathematical models and all these current microgrid models, even the controller models are being modeled in that real-time simulator. But in order to mimic the real world scenario, that microgrids are physically apart from each other, and they needs to communicate their data, sharing data from the pin node to the global controller, and then global controller will send back their set points to the pin node, so that each microgrid controller can use that to do their calculation. So here you can see that in the RTDS, we had 2 racks, and in those racks we have a GTNet card, and in those card we can use GTNet SKT module to create a socket, and those socket can exchange information to the outer world. And for the outer world, we emulated the communication network with Mininet. So you can see a representative Mininet network here. Microgrid 1 host, that is the Microgrid 1 clusters pin node. Here you can see as MG1 host, and then another microgrid clusters pin node, that is MG2 host here. So their sharing values are being then transferred via RTDS, utilizing the communication as client server method. And yeah, so the whole thing has several steps. The first step is that Mininet and RTDS needs to be synced at the simulation startup. Why? Because both, since RTDS is a separate machine, and Mininet is a network emulator which runs in the Linux environment, those can to run each other. But if the sockets are not open at the same time, they will throw error, and the data communication will be disrupted. And let's say if the Mininet starts a later time, or the RTDS starts on a later time, though the socket will be up and running in each individual RTDS or Mininet network, but they will not be able to communicate because of the broken link at that, because they are not synced. So that needs to be done properly. Then once that is done, then primary layer operates the preset reference, and the secondary layer is then activated, and the dynamic average voltage that is calculated and inductor currents are measured within the each microgrid cluster. And then from the pin node, a peer-to-peer information exchange takes place, and that data set is being then communicated to the global controller. And here you can see that this is done via the Mininet network to the global controller layer. And during this communication, we perform some attacks in the Mininet network. I'll describe the attacks in the later steps. So what it does, that then the attack is actually done in the communication link. So when the microgrid clusters leader are sending their currents via the Mininet network to the global layer, that current value can be disrupted by the attack. Again, when after the calculation takes place in the global controller, and global controller sends back the reference point calculated voltage via Mininet network again to the for the leader nodes, that is the pin node, the attack can also alter those values or interrupt those communications. So for this setup, we have selected 3 types of attack. That is false data induction. So that is actually device level attack, and this is false data is overwriting the original data set at the sensor level. So it's not, we are not using Mininet here. Mostly it's we are considering the device level, that is where the voltage and current readings are being measured. But then we consider man-in-the-middle attack. So here we introduce a rogue host that has the server and client capabilities, and that rogue host actually at first creates a server which mimics the actual recipient, that is the global controller. So when the leader node or pin node sends their voltage reading, a current reading, the rogue host alters that value, and then it acts as a client and mimics the pin node to send the data to the actual global controller. And in that way, it alters the value. And so, as I said, that all communications goes through the through this communication channel because the host is under attack. So all the communication done for this host is interrupted or altered. And then we consider denial of service attack, that is overwhelm the server with unwanted packets. So it will take up most of the computational power of the servers that is running in the either in the RTDS, that is the pin node or of the microgrid, or and also in the global controller controller. So we used ASPIN3 tools to implement this DOS attack, and it sends up lots of unwanted packet. And these packets within these unwanted packets, the actual data packets are sometimes lost because the server in the either an RTDS global node or global controller doesn't keep up with processing those packets. Yeah, Satabdy.
I think Partha, you can explain this part as well. Position.
Oh, okay. Yeah. So as I said, you can see here the communicate. We have several communities, that is the microgrid clusters here, and as Satabdy told, that each cluster have a leader node, that is the pin node, and once the pin node sends their DC current value to the global terrestrial control, and then it receives all the communities, all the clusters send their current value to the global tertiary control, and the controls calculates the VREF. As you can see, if there is an attack between, let's say, in the channel of community 4 and the global controller, both IDC value will be altered or changed or will be missing because of the man-in-the-middle attack and DOS attack. And when the VREF, so the VREF will be affected, VREF calculation will not be the accurate one. Again, when the VREF will be coming through the coming back to the all the community leaders, if there is the attack is still present there, or the rogue host or the DOS attack is still there, community leader will miss that VREF data point because of the unwanted packet due to DOS attack, or it can receive the VREF value, but it will be altered due to the man-in-the-middle attack. Yeah. Okay. So there is.
Thank you. Yes, now I take up from here. Just as Partha mentioned that the false data injection part we haven't integrated with Mininet. We did it solely on RTDS platform to verify what effect it has on our reference on the operation, on the normal proportionate power sharing operation of the microclusters. So under normal operation, it shares, the microclusters share the load currents according to their ratings, their capabilities, and accordingly the DC voltage references are generated. However, during any injected false data injection, it disturbs, it misbehaves, and there is a segregation between how they are reflected on the DC leader currents during load change and during false data injection. Next slide. Next slide. Yeah. This is for normal operation during dynamic optimization. So this part we have incorporated with the help of Partha in RTDS and Mininet. Here we have taken two DC microgrids, each containing two converter agents, and one of them is pinned. So during normal operation, we can observe in figure number C that the lambdas converge to the same value. So equalizing lambdas means having a economical operation of the microgrid clusters. And we can see that the global reference voltages are also generated and regulated around 48 volt, which is the set volt for our work. However, now we head towards the anomalies that we're trying to create. Yes, the effect of man-in-the-middle attack on the system. Here we have substituted one of the reference voltages, that is for one microgrid 1 with 50 at instant 15 seconds. So we see that the DC voltages then which are generated in the global layer, they are like go beyond the bounds of regulation percentage that we have taken, and as a result it affects the converging operation of the lambdas, and there is no optimal operating points. Next slide. So basically the system slides towards infeasible region of operation. The next is where we have taken up the effect of a DOS attack on the system. Here the behavior is that the convergence in the reference voltages generated globally and as well as locally, they converge a little bit later in time. That's a delayed convergence. And the same has been observed for the convergence of the lambda values. Next, I think we have so with that we have concluded our investigation, and these are the specifications that we have used for our DC microgrid modeling in RTDS, and the cost coefficients as well. Next slide. I'd like to conclude that we presented a way to model interconnected DC microgrid clusters in co-simulation with RTDS and Mininet. We analyze the effect of different types of cyber attacks on the effectiveness of the control mechanisms, how they are behaving, because it's important to understand their behavior, the control system behavior during the presence of any attacker. And we have come to observe that for proportionate power sharing, there might be chances of missed detection, because it just shows some transients like load change, and then it converges during stealthy attacks. And however, during MITM and DOS attacks, also it just creates a delayed convergence. And during MITM, we've observed that the system goes towards infeasibility. So it is important that keep observing all these behavior of the physical parameters with design detection mechanisms on the physical network side, so that in case of the cyber network, when it fails or whenever the protection mechanism there fails, we can avoid the maloperation from our physical controller by designing detection indices. And this work has been accepted in PEDES 2022. We'll be presenting it this month. So, next slide. These are our references for the work. And thank you. Thank you.
Thank you.
Great. So we have time for maybe one or two questions now, and then we'll do the second talk. Are there any questions for our speakers? No questions? Okay, Piyush, what you want to start your presentation? We'll start with that and see if there are questions at the end.
Sure, ma'am. Sure. Am I audible?
Yes, we can hear you.
Ma'am, do I need to share my slides or will they be?
Can you share them, or do you need us to share them?
Sure, ma'am. I'll do it. Are they visible, ma'am?
Yes, they're visible. Great, thank you.
A very good morning and very good evening to the respected faculty members and my fellow researchers in the United States and India respectively. In today's webinar, I'll talk about some aspects on how to mitigate the forecasting errors associated with solar photovoltaic generation, which is essentially a non-dispatchable distributed energy resource utilizing dispatchable distributed energy resources, which are, for example, batteries and EVs. And the case study we did for a utility in the United States, Washington. So to begin with, There is a hierarchy as far as the entire power system operation and planning is concerned. And for example, in India, there is a national load dispatch center for integrated operation of the entire nation, then regional load dispatch center for integrated operation in the region, then state load dispatch centers, and at the end, we have discoms. And similarly, in the United States, there are distribution utilities. So these discoms or distribution utilities are at the consumer end in this hierarchy. As of now, these are essentially um, not system operators as such, but they very nicely perform a variety of functions that we expect a system operator to perform. For example, they forecast the load every day in advance and share it with the system operator in the hierarchy so that they can be scheduled and dispatched. So, scheduling and dispatch is essentially a very important function in power system operation. Now, this function is also expected to be performed by discoms or distribution utilities to be DSOs in the future because now we have generation resources present in the distribution systems. Earlier, they were present only, they were connected to transmission systems, uh, the coal and thermal based power plants, hydropower plants, nuclear power plants, they are located at far end. And, but now we have resources such as solar photovoltaic generation, wind turbine generating stations. They are connected in the distribution systems. They have to be scheduled and dispatched. So they can essentially be classified into two. They could either be dispatchable, for example, batteries, electric vehicles, the power output can be controlled, or non-dispatchable, such as solar photovoltaic generation or wind turbines. Their output depends upon the the nature essentially. So how do we schedule such a non-dispatchable distributed energy source? For example, SVP panel. We forecast. That is what is being done, similar to the load forecast. But there will always be errors associated with such forecasts, no matter how accurate they are. But in real time, uh, there is a huge possibility that there might be an error, which will lead to load generation imbalance. And this imbalance has to be taken care of by system operator in the hierarchy. So, I mean, the onus should essentially be on DISCOM because the error is originating out of his control area. So, how does he handle the forecast errors so that the schedules, which are pre-specified a day ahead by system operators in the higher hierarchy, are adhered to? For that purpose, he can utilize dispatchable distributed energy resources, which are also present within its own control area, such as batteries or electric vehicles or any other type of storage. So for that, he needs to perform essentially, you can say, an economic load dispatch exercise or an optimal power flow exercise. So that is what the purpose of our work was, to develop an OPF problem that can be solved in real time within the distribution, essentially the low voltage distribution system, such that the forecast errors associated primarily with solar photovoltaic generation are taken care of. And so, such an exercise, I mean, not an OPF exercise, but has already been performed for the one of the utilities in Washington State of the United States of America. That is the Snohomish County Public Utility District. Several control strategies have been developed, but an OPF exercise has not been performed so that the forecasting errors are taken care of. Although such OPF exercises have been reported in literature, but mostly they consider all the time blocks of the, let's say there are 96 time blocks of 15 minutes each. So they consider all the time blocks together to perform the OPF exercise. So it is computationally expensive and hence it may not be feasible to do such an exercise in real time. So our contribution was to develop an OPF algorithm that can be solved in real time, essentially within a three-phase uh, low voltage microgrid, Arlington microgrid of the Snohomish County Public Utility District distribution utility, while mitigating the generation forecast errors associated with solar generation. So for that purpose, we utilized a SUMT, sequential and constraint minimization technique, the interior point method, on a rolling time basis for a three-phase low voltage Arlington microgrid for two different test cases. First, when it is connected to, we can say, the grid or the distribution transformer, and second, when it is islanded from the grid. When the microgrid is connected to the grid, we assume or we have modeled the algorithm such that the batteries and EVs are dedicated towards mitigation of forecast errors. However, when the microgrid is islanded from the grid, similar to any other OPF exercise, the cheapest available generation resource absorbs the forecast errors. So the problem is formulated such that we minimize the generation cost subject to the real and reactive power balance constraints, the inequality constraints on bus voltages, the real power output of a resource, and the inequality constraints on branch current magnitude and the current limit of a distributed resource, which is essentially the current limit of an inverter, the solar inverter. And the problem is it's essentially converted to an unconstrained optimization problem, and we need some assumptions before we apply or we perturb the KKT necessary conditions such that it leads to logarithmic barrier type interior point formulation. So at the end, it can be seen the interior point sequential unconstrained function looks very much like this. And then we solved this system, which is given by f equals to 0, the system of equations which are essentially the equality constraints in the KKT necessary, first order necessary conditions. They are solved by the popular Newton's gradient method, and then we have obtained the results. So this exercise will give the result for one particular time block, let's say for 15-minute time block. After this exercise is done, the SOC, the state of charge of the batteries and EVs are updated. And then we do this entire exercise again. So in this way, we have demonstrated the usefulness of this exercise by doing it for more than around 99 days, more than 9,000 time blocks, and it converged always. So we did this exercise for the Arlington microgrid, single line diagram of which looks like this, where there is a diesel generator, there is a battery energy storage system, there is a solar photovoltaic generator. These are the resources, and also an electric vehicle charging station. These different resources are present in this microgrid, and there is essentially a single load, Arlington office and Clean Energy Center load. So we obtained the data from the utility. We are really thankful to Dr. Sanjeev sir and the entire team of Washington State University for helping us in that process so that we could do some meaningful work for them. And the generation, SPV generation, the entire data, everything was obtained from the utility. The battery and EVs, they are assumed to be available throughout. And the initial SOC level was assumed 50% because this information was not available with us. So, and for forecasting the solar generation, we utilized Bonneville Power Administration's 30-30 persistent technique. Bonneville Power Administration is the balancing coordinator in the Western interconnection, which essentially takes care of generation load imbalance. And we utilize their 30-30 persistence forecasting technique to forecast solar generation because of its simplicity and because it leads to zero sum forecast error over the entire period of 24 hours. This will be visible when I'll show the results. And we did the simulation for a period of 99 days, 9,503 time blocks, which includes the load profile of spring and summer using MATLAB programming language for balanced as well as an unbalanced load. So the results we obtained are as follows. During islanded mode of operation, the real power balance equation, it had to be uh, reorganized, I can say, such that the cheapest available generation source absorbs the forecast errors which appear as a demand at the bus where solar generation is located. So for I think 190 for around one particular snapshot I took from the entire time series, and it can be observed that uh, in the beginning, the 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 diesel in the beginning, the battery in this, if I can do that, yes, in this particular part, the battery was already charged, so it was supplying the load. This dotted curve, black dotted curve, is the load. So initially the battery was supplying the load, but when as soon as the SOC of the battery it starts to decrease, the diesel generator starts picking up. You should remember that it is the grid is the microgrid is islanded. It's not connected to the grid, so we cannot absorb power from the grid. So hence we have to utilize the resources which are present inside the microgrid. So diesel generator starts supplying the load. Diesel generator supplies the load till the point, I mean, up to this point when the solar starts picking up. So diesel generator starts picking down. But as you can see, there is an error. There is a small error which is associated with the forecast and the actual solar generation. So it is automatically taken care of by the cheapest available generation resource. Uh, it may not be very, uh, things will become clear when the microgrid is connected to the grid. So these are the results over a larger time series. Uh, we can see that yes, during certain instances, the power had to be sent back to the grid during this particular time period. I mean, it is assumed that it's sent back to the grid, uh, but during this time periods, essentially the solar had to be curtailed because the SOC associated with both the EV and the battery, it reaches its maximum value. So no further power can be absorbed, and the solar generation is significantly more than the load. So certain either the solar generation has to be curtailed, or if feasible, it has to be sent back to the grid. Now, when the microgrid is connected to the grid, the one additional equation was included in the equality constraint, which essentially says that the the forecast errors will be handled with the help of the batteries and electric vehicles. So the difference between the forecast and the forecast error is compensated by the batteries and EVs, which are dedicated for this purpose. So it can be seen that initially power is drawn from the grid. The grid supplies the complete load of the microgrid till the point where the solar starts picking up. Now you can observe that the forecast error, which is indicated by this dotted curve, is completely taken care of by the battery. This curve is a mirror image of this particular curve. These two are mirror images of each other exactly everywhere. So whatever is the forecast error is it's completely compensated by the battery energy storage system, and it can be verified uh, from this particular point that, as you can see here, this is the forecast. So we have to follow the forecast because this is what the utility promised one day ahead. So when the solar forecast goes beyond the load only after that particular instance of time, the power which is drawn from the grid, it goes below zero. It doesn't happen here, but this is the actual, this is the forecast. So it is essentially following the forecast, not the actual. And it can also be observed from the second curve, from this particular curve, that the dotted curve is a mirror image of the battery, the power which is absorbed or delivered by the battery. So the dotted curve is the error. The forecast error is completely mitigated by the battery energy storage system. And the advantage of using the vulnerable power PPAs, power administration style 30 persistent technique, can be observed from uh, this particular, the last graph. It's that there is zero sum forecast error. So whatever SOC you start with, at the end of the day, you end up with the same SOC of the battery. So you need not worry that I will lose certain amount of storage in the battery because it has to be discharged and charged over the entire period of day to handle the forecast errors. The benefit of using VPS 3030 persistent forecasting technique is that the battery SOC level is maintained throughout for the entire 9503 time pumps. So we tried to demonstrate that it is possible to mitigate solar forecasting errors with the help of a simple OPF exercise for snowbird and for the microgrid, for low voltage microgrid. And such an OPF exercise can very easily be scaled to an entire distribution system. The MB distribution system, different with different LV feeders, can easily be scaled and adopted by the distribution utility, and also with a large penetration of EVs and SPV units at the consumer level. Now, this question might arise that if such an exercise is done for a very big system, it might become cumbersome, computationally expensive. So, in that case, it can be solved in a distributed manner, or if possible, it can also be solved in a hierarchical manner with different objectives for both distributed and hierarchical at different voltage levels for a variety of combination of economic entities. For example, we can do this exercise for a DISCOM or distribution utility at the MB level, and aggregators at the LV level, or distribution system operator at the MB level, and prosumers at the LV level in a distributed manner or a hierarchical manner, and so on. Thank you.
Okay, we have a couple questions in the chat. So you may want to put your slides back up because that refers to some of the different slides.
Sure, ma'am. Sure.
So the first question is typically how much is PV forecasting error and the size of the battery system and the EVs?
In the size of battery systems and the EVs, uh, if my slides are visible, it can be seen from the second graph that the forecast errors are not
We
very
we
much
can't see the slides yet.
Sure, I'm sorry. I'm sorry. Just 1 second. I'm sorry. Uh, are they visible, ma'am?
Yes, they're visible now. Thank you.
I'm sorry. Sincere apologies. If it can be seen from the second particular graph, the errors, the forecasting error is not, I mean, it's very less because we use BPS 3030 persistent forecasting technique. So it essentially says that the generation, the average generation 1 hour ahead, we take half an hour of 1 hour ahead, they take the average of it, and they say this is going to be the forecast after 1 hour and something like that. So forecast errors may not be very large because we use BPS 3030 persistent forecasting technique. Can be seen from here, or can be seen from here. So batteries and EVs were more than sufficient to absorb the errors. As you can see that the batteries never exhaust their capacity. The capacity is around 1.34 or something megawatt hour. So it's even less than one. So it never exhausts its capacity. I hope I have answered your question.
Ahmed, do you have an additional add-on question?
Yeah, I have. Yeah, I'm Ahmed Saber from it. Yeah. Can you say that again? What method you use? I don't get. You said that you use XYZ method for forecasting. What is the name? Say that again.
So BPS 3030 persistent technique.
BPS. What does it mean? BPS.
So vulnerable power administrations. The 3030 persistent technique, which can be that's what they use. That was reported in reference number 2. They used this technique to forecast the solar generation. So we had the actual generation, but we didn't have the forecast. So we used their 3030 persistent technique to forecast the solar output.
Okay. Yeah. So yeah, that's very good thing. And so far I
Thank you.
understand that you have PV and you forecast the PV, and if there is obviously forecasting has some error. So the error part, it means either more or less. So the balance or the difference, right? The difference will come, or it will be charged or discharged from the battery, right? So why do you
Sure.
need optimum OPF? Why do you need OPF there?
So
And what OPF does here?
sure, sir. So the when the microgrid is not connected to the grid, in that event there are different resources. present in the microgrid. For example, there is a diesel generator and there is an EV charging station. So which of these should be used? I mean, we need to use the optimal. Even when it is connected to the grid, we might utilize the power. We might draw the power from the grid if it's cheaper.
Yeah.
But in that case,
But you, yeah, but here our battery objective is to minimize the error or something for the PV, right? But you
yes,
also use the diesel. Yes. So that's another thing. So yeah, in this picture, I can see BS, EV. So your battery, the purpose of this battery is to make the balance between the forecasting error or something for the PV, right? So then,
yes.
and you also use diesel. Yes. But do you need those three also diesel?
We use
The battery
diesel.
is enough, maybe. Why do you need again
Absolutely,
diesel?
absolutely,
For
sir.
the
The battery
battery,
was
for the forecasting error.
absolutely, sir. It is.
And you
It was
told
more
that
than
you don't have that much. You don't have that much error, so the battery can sufficiently, I believe, handle those difference. So why do you need again diesel? I think you need diesel because you have maybe generation. Sorry, you have other loads, and your, let's say, load is islanded, and that's why maybe you need diesel. But the diesel you need because your system is islanded, not for
exactly.
the difference for the solar. Exactly.
Exactly, sir. During only we use diesel only during islanded operation. As you can see, it is the costliest generator. So in the island operation, we don't have the grid. Grid can be assumed as an infinite source. So when it is connected to the grid, which is here, it is cheaper than the diesel generator. So no matter whatever happens, even though BSS is dedicated towards mitigation of forecast errors, if at all we need some either to absorb the forecast error or uh, to supply power so that forecast error can be mitigated, this grid can be utilized because it's cheaper than the diesel generators.
And for the OP, unbalanced system or balance? Of course, unbalanced, right?
Yes, sir, but there was not much effect as it can be seen. There was a little effect which can be observed here during islanded operation, but during grid connected
No, I
operation,
said that it is balance, a three-phase unbalanced. It means you
it is
use ABC
unbalanced, sir.
three different phases.
Yes, it is unbalanced,
Unbalanced, and which method
sir.
you have used?
So we have
Which method you
adopted
have used for the OPF?
so interior point method, logarithmic barrier type interior
Interior
point
point
method.
method. Yeah, yeah.
Yes.
Okay, perfect. Thank you.
Thank you, sir. Thank you so much.
Okay, we have a couple other questions here on slide 11. The EV max state of charge was shown to be too low.
The EV max state of charge, it is essentially 1.34, which is the capacity of the EV, which can be seen from here. It is 1.34 megawatt hour. So although it reaches the maximum capacity at, only during certain instances, but it does, and it stays there, and only this particular time period, certain power had to be I mean, we have assumed it's sent back to the grid, but essentially what we need to do, since it is not connected to the grid, we need to curtail the solar output.
I'm seeing the black line that represents EV state of charge, and that black line appears to
Oh,
be very low. So I'm confused as to why you needed to curtail it. Thank you.
yeah, sure. I'm sorry, sir. I mistook EV for battery. This is essentially because the EV, the capacity is only zero point 0.1 megawatt hour. So it's probably here, somewhere around here.
Okay, thank you. The megawatt hours is the proxy for a state of charge, and it so happens the EV is 0.1 megawatt hour, and the battery is 1.3 megawatt hours. Now I got it.
Yes,
Thank you.
yes. I'm sorry, sir,
No,
if I
no,
missed.
please. No, don't apologize. You're doing great. The second one is there one BESS and one EV in each phase? In slide 12, you had BESS
Yes,
phase A, B, C.
yes, sir, absolutely. The same capacity, BSS and EV were connected in each phase.
Thank you. In slide 13, what did you mean by battery SOC level has to be maintained? It seems like, okay, now that I know that is not SOC percentage, it is megawatt hours. So it is
Yes,
being maintained between 50% SOC and 100% SOC, is it?
yes, sir, exactly. I mean, this is
Thank you, sir. Thank you very much. Appreciate it.
Thank you so much. Thank you.
Okay, I think that's all the questions in the chat at this time. Does anybody else have questions on this talk or on the first talk? Okay, well, we are very appreciative of our speakers today for being, for our student speakers today. It's great to see the collaborations between our India partners and our US partner universities. So thank you very much to our speakers today. We will not have, this is our November and December webinar. So because of the holidays, our next webinar will be at the end of January. So we appreciate all our speakers and for their time this year in 2022. And we wish everyone happy holidays and all the best in 2023. So if anyone's interested in giving a talk on some of their work, please feel free to reach out to Tiffany and myself and we will get you signed up. So thank you all very much for joining us and good night to our India colleagues, and for our US colleagues, have a great Thursday.
Thank you, Professor Shields.